In our discussion about the ASD methodology for determining wind load, I first want to point out the Helvetas manual, which gives us a 0.5 kilonewton per meter wind drag loading. This is based on the 160 kilometers per hour or 100 mile per hour velocity, design velocity horizontal to the walkway, and is equivalent to 1.3 kilonewtons per meter squared of pressure acting on the equivalent 0.3 meters squared of solid area per 1 meter squared of area. And this is what the manual specifies and comes down to the number 0.5 kilonewtons per meter as a line load. However, this is not enough information and includes various assumptions that aren't specified in the manual. So in this lecture, we're going to backtrack to the ASCE specifications to dig even further. And in order to arrive at a similar number as above, we can dig into these assumptions and do a more in-depth analysis with ASCE 7 for other structures to calculate wind pressure, which is in chapter 29. And like most prescriptive codes, this is a probabilistic analysis of wind forces. First, to find drag forces perpendicular to the bridge, we'll look at the ASCE other structures and signs, and first calculate QZ from 29.3.2, the velocity pressure at a specific height. So that's this equation here. The variables to calculate this equation are KD, the wind directionality, KZ, velocity pressure, exposure, KZT, the topographic factor, and V, basic wind speed. Each of these are calculated as follows. KD being we're assuming an open sign and lattice structure, we'll take 0.85. KZ, we're going to assume the structure is up to 50 feet high and is exposure category D, so we'll take 1.27 according to the table. Assuming conditions are not meant to reduce this factor, we'll take KZT equal to 1.0, and as specified, our basic design velocity or basic wind speed is 100 miles per hour or 160 kilometers per hour. With all of our coefficients specified, we can calculate QZ at the height of 50 feet, to be approximately 27.6 PSF. Then in section 29.5 for other structures, we can then go on to calculate P, our pressure. And this is a slight modification of the equation for F in the text, and we're just going to take out that area term and add it in later. And with that, we have two more new variables, G, our gust factor, and CF, our force coefficient, similar to drag coefficient. And we calculate those as follows. In section 26.9, we get G specified as 0.85. And in table 29.5-2, for a flat-sided object, we can calculate our drag factor to be 1.6. And this is from calculating a solid to gross area ratio of approximately 0.31. This is using the W1 walkway detail, which is like our worst case scenario. It has the most exposed profile area. I won't go into the calculations in this lecture, but you can navigate to that detail and use that, use the geometry to calculate, how much solid area we have per gross area. And a good resource for calculating that is also added in this module as a textbook, and is a resource for calculating the solid area of chain link fence. Other than using those factors, it should be pretty easy to use the profile of the detail to then calculate what our total solid area to gross area ratio is. And then we'll calculate our pressure P to be approximately 37.6 PSF or 1.8 kilonewtons per meter squared. We'll multiply by walkway height, and then we'll multiply by the ratio of solid to gross area again. And remember, here, we're going to count the chain link twice. And that should give us an approximate horizontal load of 0.37 kilonewtons per meters. Additionally, I can calculate or I can also count the cable area twice. And that'll bump my number up to approximately 0.43 kilonewtons per meter, which is even closer to that 0.5 kilonewtons per meter that we get from Helvitas. And this is a good check that we're actually under that value. We don't want to be over that value because then we've been using a number that is too small.